Before you watch this video, make sure you watch the video on the wolves of Yellowstone Park that is included, the link is included in the comments to this video and the previous first part of this lecture's video. But a quick recap is the wolves of Yellowstone Park were killed off in the 1920s, and a lot of different reintroduction of the wolves initiatives finally paid off, and the wolves were brought back in the 1990s. However, before that happened, ecologists had to make sure that they had a solid case for the reintroduction of the wolves, and in particular, that they modeled carefully how many wolves to bring back. What questions did they really have to consider while making their analysis? Too few wolves, and the pack won't be able to hunt effectively. Too many wolves, and they will kill off the elk and therefore themselves not survive. So the questions that they had to consider had to be both on the prey and the predator side. We, in our analysis here, are going to make a few simplifying assumptions. The situation is very complex, and we're not going to be able to consider every single factor, so we're going to work with the more simple version of the problem that actually is in Yellowstone Park, and a slightly simpler model than the ecologists worked out for themselves. Just like in the case of the spherical cells, that would mean that based on our assumptions are going to be our conclusions. And so our conclusions will only work within the system that we ourselves have built. And we're going to have to be careful about that. One of the simplifying assumptions we're going to make is the only predator and prey we're going to consider are the wolves and the elk. It is a multi-predator system, and we will make small adjustments keeping this in mind. But in general, we're only going to think of the two present actors. The prey is the elk, and the predator is the wolf. Then we're going to really have to think about how wolves behave as predators. How often do they hunt? How much do they have to hunt in order to survive? Do they keep hunting if the prey is present? We know that there's a lot of elk, so will they just continue killing off the elk for no reason whatsoever or not? We're also going to have to model the elk population. How do they reproduce? How often do they reproduce? And again, we're going to have to be careful about thinking in terms of suppressing the elk population, not killing it off entirely. So let's start off by thinking about the types of predators and where wolves fit into that picture. In general, there are three main types of predators, and this is what we call a predator functional response. Functional response essentially to the density of prey present in the area. This is also called Halling response, named after UBC researcher Halling. I encourage you to once again read up on the people behind these models and these discoveries, because in particular, Professor Halling is, of course, local, and so it's interesting to see how their career has developed within the Canadian and particularly British Columbian context. So, as per the Halling response, there are three types of predators. Notice that the axes here correspond to prey density. So this is low prey density, the prey is scarce, and this is high prey density. So prey is available everywhere. And the predation rate. So what happens, how does the predator behave depending on how much prey is there available? And we see the three different types here. Before we even really start thinking about what kinds of predators these might actually be, purely mathematically, we have ourselves three different graphs, and purely mathematically, we can already come up with the types of formulas that can describe these graphs. So for type 1 here, we can see that the function is clearly just linear, right? Just a linear function, so something like y equals kx for slope k. For type 2, we see that the behavior near the origin is matching type 1, so this is a very linear behavior here, but then the function steadies out and plateaus towards a horizontal line. So this, of course, is what we've already seen as the linear hill functions. So this is likely modeled by ax over b plus x. Type 3 also has the hill function form. It starts off having a very different near origin behavior from type 2, but it levels off to the same horizontal line. Notice, of course, here that because the type 3 is much flatter near the origin, it means that the degree of it is higher than the type 2 hill function. So here, though, it's not clear exactly what it is. It could be quadratic, it could be cubic, it could very well be a fourth degree polynomial. It is some kind of higher degree of a hill function. So normally we would say that this is, for example, squared or cubed hill function, or again, maybe some higher power of x. The graph is a little bit misleading at the end because the higher degree hill function will eventually cross the lower degree hill function. So the scale just hasn't been extended the window hasn't been extended far enough to accommodate for that. Okay, so now let's think about what kinds of predators are described with each of these types of functions, and can we think of the actual examples of real-life predators that follow these particular behavioral patterns. So for type 1, what characterizes this function is the fact that no matter what happens to the prey density, the predator simply keeps hunting. They keep eating. They keep finding prey everywhere, and every time they find it, they continuously consume it. So this means that the more prey is available, the more the predator will eat. This is, of course, very different from the other two types, type 2 and type 3, that end up plateauing. So no matter how much prey is available, the predation rate stabilizes at some number, which means that the type 2 and type 3 predators actually get satiated and stop hunting, as opposed to type 1 that continues to consume its prey. Okay? Type 2 and type 3 get satiated. Now we have to differentiate between the type 2 and type 3. So while their end behavior is the same, their near origin behavior is quite different. So for prey density near the origin, what happens here? Look, if we are in type 2, then for small prey density, the predation rate increases immediately. So the predator, again, at the end gets satiated, but also prey is quite abundant. Even for small density of prey, the predator is able to hunt quite efficiently. Whereas for type 3 here, for small density of prey, the predation rate is quite low, which means that when there is very few prey, they are in fact hard to find. But once they're found, the predator hunts them, and again, doesn't continue hunting, actually stabilizes their behavior. So here's the general summary of the three types of the predators. First, the more prey is available, the more predator eats. Second, the predator does get satiated, and there is a clear abundance of prey sort of available at all times. And type 3, at low density, prey is hard to find, but the predator eventually gets satiated if the prey is in fact available. Let's think of examples of each types of predator that we can come up with from, our real life experiences. So I encourage you to pause your video for a second here and actually think of examples that match type 1, type 2, and type 3 predators from real world animals, mammals, fish, whatnot. To me, the first type is always the hardest to think about right away. The more prey is available, the more predator eats. When I think of predator and prey, I generally think of the hunting type of predator. Whereas the type 1 here actually corresponds to something quite different. Some examples are elk and grass. So maybe the actual prey doesn't have to be an animal, it could be a plant. So elk and grass here. Another example where everything is an animal will be whales and krill. Right? They constantly actually consume krill as they keep going because they consume it in such small amounts that they have to continue eating it as the density goes up. One of my students from last time I taught the course said that kids and candy also fall into the type 1 predator. The more candy there is, the more candy the kids will eat. Type 2 predator. There is always an abundance of prey, which means that basically the predator doesn't have to really hunt. They are able to obtain prey whenever they want, but they do eventually get full. So they don't keep eating it, they stop gathering, let's say, the prey. Not so much hunting because it's available so freely, but gathering. So some examples include, let's say, bears and salmon. When they're hunting it through the summer, the salmon, especially when they're going up the river, are readily available. So the bears don't so much hunt them as simply catch them, but they do get satiated. And finally, type 3 is at low density, the prey is hard to find, but predator eventually gets satiated. This is what I would think of as the most standard example. So things like lions and caribou, everything that you see on the Discovery Channel, or as in our case, wolves and elk. Wolves and elk. So now we've figured out that our wolves are the type 3 predator, which means that they're modeled by one of the higher degree hill functions. And now, with that in mind, we can actually figure out the function that models their behavior. So the data I'm going to give you is based on field studies of the behavior of wolves and elk, and also made to fit whatever field studies have produced in terms of the actual numbers. So predation rate. How much elk do wolves actually have to eat to survive? Generally, in order for an adult wolf to survive, they will need about 2 elk per month. So per wolf per month. Now this, if we're thinking in terms of the yearly amount, is going to be 24 elk per wolf per year. But this is where we can refine our numbers a little bit. The wolves actually need 2 elk per animal per month to survive. However, let's think about it. A pack hunts for the elk, they catch the elk, they eat however much of it they are going to eat in one sitting, and then they leave the carcass behind. They will come back the next day and eat a little bit more, and so on and so forth. But in between their meals, other scavenger animals will come in and also actually consume the elk that the wolf have hunted. So in terms of how much they have to hunt, it's going to be more than 2 per month, because in order to eat 2 per month, you have to kill more than 2 per month. So we can adjust this 24 a little bit. Let's say we're going to round it off to 30 to account for whatever scavenger animals are present and are going to somehow benefit tangentially from the wolf's hunting. We're also going to assume that the predation rate is modeled by a cubic hill function. So some coefficient x cubed over some coefficient or some constant plus x cubed. So now, where does this 30 fit in? They need 30 per wolf per year, so no matter how many prey are available, the actual wolves will only need this many elks. So this is our plateau behavior. This is our horizontal line that the predation rate will approach for large values of x. So take a minute here, pause the video, and try to think about where does this 30 fit into this formula. If I insist that the coefficient in front of this x cubed is 1, how can we make sure that the horizontal asymptote, the value for large values of x that the predation rate approaches, is actually 30? Okay, it shouldn't be too long to figure out that this a should actually be 30. Now for the value of b, I'm not going to show you the calculations, I'm not going to show you the field data, but the field data fitted to this model suggests that this value for b is going to be quite large, approximately 20 cubed. Okay, a very big number here, so a function is going to be really quite flat near the origin. Okay? Now, in terms of prey reproduction rate, I have to make sure, essentially, that the predation rate is somehow balancing off this prey reproduction rate. So I have to think really carefully about how often and how much the prey actually reproduce. And the general population of elk will have approximately 1 calf per year per female. So they only actually give birth once a year. And the females that give birth have to be at least 1 year old. Okay, so not every single female in a herd will produce 1 calf per year, only those that are old enough to do so. Very rarely will there be 2 calves per year. That's a very rare occurrence. More often, it's going to be on average less than 1 calf per year per female, because not all of them will survive to sort of adulthood, let's just say, of any kind before they get a chance to be eaten by wolves. Now, if it's per female, we also have to think about how many females are there in a herd, and approximately 70% of any herd is actually female. So that means that if there are X elk altogether, 70% of the herd is female. So 70% of them are eventually going to be able to reproduce. However, they only reproduce after they've reached a certain level of maturity. So not every single female will be able to get to be to reproduce the following or in any given year. And also not all of their calves will survive immediately. So taking all of this into account, if I have X elk, 0.7x will be a sort of largest possible value for the reproduction rate, but it's of course going to be less than that because I have to account for the fact that some of the females in the herd are too young to reproduce. So overall, I'm going to say that the prey reproduction rate is about 0.55x. Okay, so I've dampened this number down by a little bit to account for the maturity level and for sort of the small amount of infant calf deaths. Okay, so what is the prey density? I have that this is how often they are reproduced, and this is how often they get eaten. So essentially, the prey density is the difference between these two factors. And it doesn't really matter which order you subtract them in. You're just going to have to adjust your analysis or your final interpretation of your analysis based on whether you subtracted births from predation or predation from births. Doesn't really matter. The questions to consider here are, for what prey density is prey most in danger? Because we want to avoid that. And for what prey density is predator most in danger? We also want to avoid that. In fact, what we really want is the case when these two are completely balanced out. So I would like to reach an actual constant level of predators preying, the prey reproducing continuously, but not growing. So that means that whatever the prey reproduction rate is, it actually has to even out with the predation rate, and each of them will suppress one another. So what I'm really interested in is where these two quantities are equal. Okay, let's take a look at the graph of the graphs of these two functions. So the red here is my predation rate and the blue is the prey reproduction rate. So I notice that I have several points of intersection here at 0. Well, that's not really surprising. If there's no elk, then there can be no wolves, right? There's nothing for them to eat. They will essentially die off before getting any kind of chance of survival. And then there's other 2 points of intersection, somewhere near 14 and somewhere near 52, okay? Later on, we will discuss the significance of these 2 points, but both of those points actually correspond to the balance in the ecological system. At both of those points is when the predation rate is equal to the prey reproduction rate, and therefore ecological balance will actually be restored. It's just one of them will be sort of a little bit more dangerous than the other, and it's going to be the higher point. At this higher point, we're going to see that a little misbalance, a little to the left or a little to the right, will kind of wreak havoc, whereas the smaller point is going to be the one that is a more stable equilibrium. This smallest point is around 14. And in fact, the ecologist from the Yellowstone Park brought back a pack of wolves that were 12 in quantity. They brought back 12 wolves as one of the packs. They later introduced another pack of, I think, another 12 wolves, but in a completely different area of the park. The first pack was 12 wolves. Our result here, based on very rough analysis, is 14. Isn't this amazing? With very bare tools that we've been able to develop so far, and with very rough field data, we were already able to get really close to the answer that the ecologist got to in order to actually introduce wolves back into the Yellowstone Park. This is the real power of mathematics. We're taking very simple assumptions and turning them into something that we can model for in the real world. The other real strong point of mathematics here to think about is the fact that we used the power functions, and in particular Hill functions, to describe the predator-prey dynamics right after we used them to describe chemical reactions. The exact same type of function described 2 very different world phenomena. This is the true strength of mathematics. Just by studying the behaviors of different functions, we can model all kinds of things in the real world using the exact same mathematical tools.